Okay, here's another integral that you may have seen in Calc 2. Sine x divided by x. The function itself, sine x over x, this is called a sinc function. And it has some very useful applications in communication theory and Fourier transforms and stuff like that. Let's see, if x goes to 0, what's the value of this function at 0?
1.
1, right?
It limits to 1.
Yeah, if you send x to 0, sine of 0 over 0 has a limit 1. Okay, so although the graph is not defined at 0, you have an open circle there, right? It does give you 1 as a limit. And because sine function is like, it's like this, right? So you get something that's oscillating, but the amplitude of the oscillation is 1 over x, so it's getting closer and closer to 0. So you have such a thing.
Because the derivative of sine 0.
Yeah, so you can use the L'Hopital to evaluate that. If you want to send x to infinity, x to 0, then the 0 or 0 type, you can use L'Hopital. Derivative of sine is cosine, derivative of x is 1, so cosine 0 is 1, so that's why I did. And usually when you say sinc function, you fill this removal of singularity as just 1, and that's called the sinc function. So the sinc function will be a function that's differentiable, actually. It's smooth and differentiable. On the other hand, if you have the integral from 0 to x of sine t over t, this one is called a sine integral function, or I guess sine si. And I frankly haven't seen this being used, but people tell me that this function is used in optics. And in physics, there's a subfield called optics. They use that here. Okay. But in either case, the actual antiderivative of sine x over x, that cannot be expressed in terms of basic elementary functions. You can't take all the functions that you know, like log, exponents, sines, and cosines, sine hyperbolics, whatever you name it. You can't add them, subtract them, multiply, divide, or you can, no matter what kind of operation you do between them, you cannot express this in a closed form. It simply doesn't exist, okay? And you can verify that that's true by plugging this into Wolfram alpha. It will not give you the answer. It will refuse to give you the answer. I think it might give you answers in the error function. That's when you may have seen that, okay? Because after all, sine is like via the Euler identity, this is really difference of 2 e to the ix minus e to the negative ix. So it has something to do with the exponential function, and then you can do some change of variables, and you end up with some error function there. Okay. But anyways, so we do see that that's an even function. That's like that. It goes to 0 like that, and maybe even if you can't find the antiderivative, the actual integral from negative infinity to infinity may exist. Who knows, right? Okay, so how do we do this? Well, first, we have to, and actually this is a quite hard question, so we have to do multiple steps, okay? So first thing that we have to compute is the integral from 0 to infinity of e to the negative st times sine of t dt.
Well, what is the s?
S is a fixed constant.
Oh.
Yeah. And you know, eventually we want to differentiate by s because we're doing what's that? Feynman trick.
Are there the same thing, or there is a new question?
Oh no, we're going to start here. Eventually we'll like do all kinds of computations, and then we'll bring back to here. Okay? Yeah. All right. Who has seen something like this before? Nobody. Okay. I sometimes question, do I really have the right students here? You claim to haven't seen anything here. Oh, that's called the Laplace transform of sine of x, sine of t, right?
Yeah.
Right? What's the Laplace transform of f of t? This is from 0 to infinity of f of t times e to the negative st dt. Okay. So, I mean, in fact, you can just look up the Laplace table I handed out everywhere to everyone today, and find the answer. What's the answer? No. A Laplace transform is sine t. What's that? You should know how to read the table at least.
It's
S
not.
squared 1 over s squared plus k squared.
Yeah.
And
What the
one
k
squared,
mean?
squared, one squared.
K mean 1, right?
1.
That's the one. Okay. Well, so that's how you do it. But I still want to show you how this is done because I've only shown you tabular integration when the last row is 0. So this is a nice example where the tabular integration doesn't terminate to 0 and you have to figure out what to do. And again, we can use the Lie formula. Logarithms, inverse trigs, algebraic trigs, exponential. Sine is a trig, and this is an exponential. So this belongs to the right side, which means it belongs to the integral column. So I put e to the negative st. And then trig is on the left of e, so this belongs here. Okay, now we differentiate sine, you get cosine. Differentiate cosine, you get negative sine. Now you realize what I mean, right? It doesn't terminate to 0, it just repeats. Okay. So what do we do? Well, you stop at the third row. It's something that you just have to know. That's the downside of the tabular integration. You might be wondering, like, if tabular integration was so easy, why didn't they teach you in Calc 2? Well, because it sometimes it's not so straightforward to use. Okay. So this is an example where it's not so straightforward to use. So you have to stop at the third row when you see the first function back again. Okay. Whenever you see the same function appearing again, stop. Right. Okay, so plus, minus, plus. Now we have to integrate. If you integrate e to the negative st, you get negative s1 over s e to the negative st. Integrate again, you get 1 over s squared e to the negative st. Right? So every time you integrate, the reciprocal of this thing in front of t would pop out, right? So that's why you get that. Now let's try to extract the result of the tabular integration. And this last line not being 0, that's going to create something that you haven't seen before. Okay. So this goes down here, which gives you negative 1 over s e to the negative st sine t. And then do this across and then 45 degrees downwards. That gives you negative 1 over s squared e to the negative st sine t. And then there's one extra thing that you have to do, which is to go the other direction.
Minus.
Yeah.
It's not
Which
cosine
is-
t?
Huh?
It's not cosine t?
No. You do straight
No.
across.
The second term.
The second one is
Right under
Second
Oh.
I'm sorry.
Thank you.
Cosine.
Thank you. That's important. Okay. Yeah. All right. So now you go this way, and what do you get? You get negative 1 over s squared e to the negative st sine t, right? Agreed? But this last line that you went this way has to be integrated. It's treated differently. Okay? Okay. So, what does this result say? It says, well, what I'm doing is not a definite integral. I'm doing the indefinite integral first. So, the result of the integral goes like this. If you integrate e to the negative st sine t dt, that's going to be equal to negative 1 over s e to the negative st sine t minus 1 over s squared e to the negative st cosine t plus this one, but let's bring this negative 1 over s squared. That's a constant because you're integrating by t, so s is just some constant which I can bring it outside, so it'll be negative 1 over s squared integral of e to the negative st sine t dt. Okay, so that's the result of our tabular integration, which is a bit weird because we are trying to look for this and look at the answer. The answer contains what you wanted to know. So it's like a circular reasoning. You asked a question and it answered where the answer contains your question. So at first this seems like we're getting nowhere, but how do we do this?
Add the
Yes, we bring this over to the other side and then say 1 plus 1 over s squared, which by the way is s squared plus 1 over s squared, okay, times e to the negative st sine t dt is equal to, let's rewrite this with the negative e to the negative st factored out, okay? Factor that out and then get 1 over s sine t plus 1 over s squared cosine t.
yeah.
Okay? All right. So we are almost there. Now, let's simplify. Let's solve for this unknown. See, we're trying to find this one, right? So we just have to multiply the reciprocal over to the other side so that it will be e to the negative st sine t dt equal to negative e to the negative st. See, multiplying s squared to 1 over s will give you s sine t. Multiplying s squared to 1 over s squared will cancel the s squared and you get cosine t. So that's what's going to happen if I multiply s squared both sides. But now you have to divide by s squared plus 1. So this entire thing would be divided by s squared plus 1. Okay? And now let's plug in the endpoints. So I want 0 here, infinity here. So you get infinity here and 0 here. Okay? So what? Well, first, I forgot to assume that s is some positive number, okay? And in fact, you're going to assume that s is some big positive number. So if you plug in infinity here, what do you get? You get e to negative positive times infinity, which is e to negative infinity. What's that? E to the negative infinity is? 0. So when you plug in infinity on this side, it'll give 0. Then minus negative, and then you plug in 0 to t, so it's e to the 0th power, s times sine of 0 plus cosine of 0, because you're plugging in 0 into t. Negative, negative is positive, e to the 0th power is 1. So times 1 doesn't do anything. Sine 0 is 0, cosine 0 is 1. So you get 1 over s squared plus 1. Exactly as your Laplace table says. Okay?
I think we do some questions with this trick and by
Right.
parts.
Yeah. Okay. So we have that. Now how is this related in any way to what we are trying to do? So we're going to put this as 1 over s squared plus 1. Okay. So what we are trying to do is, now we're going to define I of s as 0 to infinity of e to the negative st sine t divided by t dt. I can't imagine who first thought about this. I would never be able to think this without seeing someone do it. Yeah. Another very big surprise. Right? Yeah, who would think this? Now, how is this one related to this one?
It's just multiplied by e to the negative st, right?
Right. If you plug in 0 to s, you get sine t over t. Now, because this is an even function, you just have to double this value. So this thing, whatever that is, if we can figure that out, this will be I of 0 multiplied by 2. That's what we'll get. Right? Okay. So are you fine so far? Okay. So now let's do the Feynman trick. What's the Feynman trick?
Derivative of s.
S. See, this is a function of s, so we differentiate both sides by s. Okay? So we do I prime of s, differentiate as a function of s. And what does that bring down? Negative t, right? Yeah. See, if you differentiate this using the chain rule, it'll be e to the negative st times negative t sine t over t dt. And then t cancels. You can bring the minus outside. Oh, what a surprise. What is this?
1 over s. No,
That's
negative
it.
1 over
It's-
s
yeah,
squared
yeah.
plus 1.
It's exactly the same thing. Right? Okay. Therefore, I of s is just the antiderivative of this. What's the antiderivative of 1 over s squared plus 1? So do you remember integral of 1 over 1 plus x squared? Does anyone remember the integral of this? Not log.
Arctan?
Arctan, yes, that's the arctan one. So because there's a minus, it will be negative arctan of x plus some constant c, which we have to figure out. Okay. Okay. Now, what we do is then we think about limit of s going to infinity of is. What's that? So that one can be just observed here. If you take s to infinity, t is some positive value, right? T is from 0 to infinity, so t is some positive value. So what happens to this one if you send s to infinity? It will become 0, right? If s is the bigger the s becomes, this will become smaller and smaller, right? So it will eventually become 0 at s going to infinity. Right? So I know that this limit has to be 0. Okay.
Does that mean the constant
Should be
0?
no.
No.
What is arc
The
tangent
constant is arctangent x?
of infinity? What's that? Okay, so here's a graph of tangent. Y equals to tangent of x has these asymptotes, right?
Okay.
Now, if you're given a graph, how do you draw the graph of its inverse?
It is down.
You flip over the y equals to x, right? So it flips this way, right? And one of the effect is that the vertical asymptotes become
The horizontal.
horizontal asymptotes because you're reflecting over the diagonal, so it's going to be 1, negative 1, okay? It'll be like that. Okay. Oh, not 1 negative, pi over 2, negative pi over 2. Yeah, because you had vertical asymptotes at pi over 2 and negative pi over 2. You will have horizontal asymptotes at pi over 2 and negative pi over 2. So what's the limit as x goes to infinity?
pi over 2.
Pi over 2. So if you send x to infinity, you get negative pi over 2. Therefore, c must be
Pi over 2.
positive pi over 2 in order for this to happen. Right? So see, this one here would be equal to negative pi over 2 plus c, because if you send x to infinity, arctangent of infinity is pi over 2. So you get negative pi over 2 plus c, that has to equal to 0. So these together, you get c equals to pi over 2. Okay, so now we know what this is. We know that this unknown thing, which looked really complicated, actually had a closed form, which is it's negative arctan of x plus pi over 2. That's the result that we got. So I of 0 is what? Oh, not x, sorry. It should be s. Kept using x there. Yeah, sorry. Okay, so if you plug in 0 into s, what's arctangent of 0? It's here, right? What's arctangent of 0?
0.
0. So you get 0 plus pi over 2, which is pi over 2. But this is integral from 0 to infinity. What's the integral from negative infinity to infinity? Pi. Okay? So that's the result.